Ladies and gentlemen, it's time to make a start. My name is Andy Schofield, and I'm the Pro Vice Chancellor and Head of the College of Engineering and Physical Sciences. And it's a great pleasure to welcome you all to the Engineering and Physical Sciences Distinguished Lecture Series. As many of you are connoisseurs of this series, it probably doesn't need too much introduction, but the idea is that we scour the globe for the best scientists and engineers who can give us an insight into their work. And for this particular lecture, we haven't had to search too far for a world leader in their field, and it's a really great pleasure to introduce our speaker today, who is Professor Dave Charlton. Dave will be known to many of you. Indeed, he tells me that there are some in the audience who will remember him as a graduate student. So he did his PhD here at the University of Birmingham, and his career has flourished from that point, although it's actually oscillated spending time at Cern. And if he isn't quite as familiar to you on a daily basis as some of the other academic staff within the School of Physics and Astronomy where he's based, that's because, as you will hear in a minute, his time is very much taken up with his work on the Atlas experiment at the Large Hadron Collider. But Dave's cut his teeth in particle physics on the UA1 experiment, which was another very impressive experiment which deserves its place in building up our understanding of the Standard Model. I'm sure we'll hear more about the Standard Model in Dave's talk. And then was involved in the Opal experiment, and then in recent years was involved in what he's currently doing now, which is working on the Atlas experiment. And Dave was the physics coordinator in that experiment. He then became the deputy spokesperson and is now in his second term as the spokesman for that experiment. And modesty will forbid him from telling you this, but being spokesperson of the experiment is not just a title, but it actually means you are the person responsible for running that experiment. And if you think about the scale, and part of the talk is about the scale of that experiment, it's a truly gargantuan activity. 3,000 people involved in this one experiment from a whole range of countries. And if you think about the scientific endeavour over the last 200 or 300 years, there really is not an experiment that has that sort of scale of activity. And to have not just a British physicist, but a British physicist from the University of Birmingham running that experiment is really a truly impressive achievement, and we all glory in it. And also, as you can tell, but also others recognise that leadership. And Dave was, in 2014, elected to a fellowship of the Royal Society, which we also celebrated. Enough from me. The programme for the evening is Dave will speak for roughly 3/4 of an hour, and then we've got about 15 minutes for questions from the audience. But then Dave is also going to be in the room opposite, where there will be refreshments for us all. But if you would like to ask your question in a less public atmosphere, then there is ample time to do that. So without further ado, let me introduce our speaker, Professor Dave Charlton.
So thank you for those very kind words of introduction, Andy, and indeed it's a pleasure to be, as Andy has mentioned, I spend most of my time actually at Cern just at the moment, but it's really a great pleasure to be back in Birmingham to tell you about the work we're doing on Atlas. So you see the title of and the subtitle of my presentation, Fundamental Science with the World's Largest Scientific Instrument. It's a little bit debatable, that issue of whether it's the world's largest scientific instrument, but it's certainly one of them. And I think you also will realize recently that it's not just in particle physics, but also in other areas of physics, for example, with LIGO and gravitational waves, where very large-scale science is really delivering now a lot of very exciting results. So let me start at the beginning, which is everyday matter, and let me just run through you. This will be a bit pedagogical for some of you, but let me remind you that inside matter is made up of molecules at the level of nanometer sizes, and atoms at the level of tenths of a nanometer, angstroms. And then deep within the atoms there are nuclei, and the nuclei themselves are made up of protons and neutrons. And these are at the scale of 10 to the minus 15 meters, which is a millionth of a billionth of a meter across. So these are pretty small things. However, in particle physics, what we're looking at, particularly at the Large Hadron Collider, is we're not looking really at protons and neutrons, we're looking at the constituents, and we're colliding together the constituents of protons and neutrons, and we're looking at length scales which are 1,000th or less than the size of a proton. So in terms of the science we're looking at, protons are gigantic, huge, great composite objects, and we really want to look at the little things inside. So let me then show you the forces of nature. So particle physics is very much the study of the constituents of matter, but also of the forces of nature that they feel. And so the electromagnetic force is a very familiar one for people with engineering and physical sciences background. I don't need to tell you about the electromagnetism. It's carried by the photon. And then, in addition, of course, there's the weak nuclear force responsible for stellar burning, which is carried by the W and Z particles, and the strong force which binds together the nuclei carried by the gluons. And so we're really looking at both the particles and the forces. And one of the themes that's been happening for the last 150 years is to try and unify these forces together in a consistent mathematical framework, which will be part, don't worry, I won't show you too much of the maths, but nonetheless, the idea of trying to unify the description of particles and their forces in consistent frameworks is very fundamental to particle physics. So here is the standard model of particle physics on one slide. Of course, it's a bit more complicated than this if I write down the equations, which I won't. But here, what you see here is you see the particles, the quarks and the leptons, as we call them, the matter particles, of which there are actually 6 of each. There's the up quark, the down quark, the electron. Those 3 essentially make up the everyday matter. But then in addition, there are these heavier partners, the charm-strange top-bottom, and the muon, the tau, and then 3 flavors of neutrino, very light, very neutral, almost uncharged particles. And so these together form the matter particles, and these are so-called fermions in our jargon. For the physicists, they have half-integer spin. And in addition, there are the particles which carry the forces, so the WZ, the photon, and the gluon, which are bosons. They have integer spin for the physicists. And until 5 years ago, this was where we were, and at that point I used to show a version of this slide which had a big question mark here in the middle. Now, of course, we know what that is in the middle, and we know about the Higgs boson, but I'll talk more about that in the remainder of this talk. But this is basically the picture of the standard model, and many of the questions that we are now looking at are, is this it? Is that physics, or is there much more to physics than this? Is there much more to fundamental physics than this? Are there more particles? Are there more forces? How do we unify forces, etc.? So let me turn first of all to the mystery of mass, and the first part of the talk, the results I'll talk about, will be related to this. So it's difficult to explain this a little bit in everyday terms, but we have these force-carrying particles I talked about, the photon, the W, and the Z. They have very, very different masses. They weigh a very different amount. The photon is completely massless, and so it flies around the universe with the speed of light with no problems if there's no material in the way. But the W and Z particles, these have a mass of 80 or 90 times the mass of a proton. So these are like the equivalent of heavy nuclei in terms of their mass. They also decay very fast. But in the mathematical framework we have, in the standard model, these 3 guys actually are all part of the same force. And so there is a theory, there is this theory which has some rather beautiful mathematical symmetries, which I can't go into detail, but it works very beautifully to unify these forces, but provided that the particles have no mass. Now, problem, of course, that this is not what we see in nature. These particles, except for the photon, they do have mass. And so one has to find a way, I mean, the idea that came from Braut, Englert, Higgs, and others, Guralnik, Hagen, and Kibble in 1964, was perhaps there's a way around this, a way to put a trick in the theory which allows you to have masses to the particles without breaking these beautiful symmetries of the theory. And this is the so-called the BEH mechanism, as we tend to call it, although you may know it as the Higgs mechanism. And it has basically one simple idea, which is that the vacuum, everyday space-time, is not empty. I mean, it is empty in terms of what you or I would call empty, but there's something there. There's a field there. There's some property of the vacuum which breaks the symmetry, that provides a very unusual, I mean, it sort of sits there as a uniform thing which is there in any things that we call the vacuum, empty space, actually has this stuff in it. So that is the basic of the mechanism. This stuff that's there, the Higgs field, it actually interacts with particles, and it interacts according to their masses, and that's the fundamental idea of the Higgs mechanism. But as a corollary of this mechanism, one has to introduce an extra physical particle, which is the Higgs boson, at least one. Okay, another way of looking at the science that we do is shown in this particular slide. And this is the history of the universe in one slide. I hope this is all right if I point a bit. This is the whole of the universe, the history of the universe, the whole of space-time in one slide. We, of course, sit here down at this end today, about 13.7 billion years after the start of the universe. If one looks back in time, the universe was smaller because the universe is expanding. And there is a certain time, 300,000 years ago, for example, when atoms, the energy density of the universe was so high that the temperature of the universe, if you like, was so high that atoms couldn't form, atoms broke up. And at that point, actually then, matter started to get all mixed up and everyday matter didn't exist. That was when the cosmic microwave background started to appear. You go back further and even the nuclei of atoms and even then the protons and neutrons all started to merge together until you just had this big soup in the early universe. And the energy density conditions that we're creating at the LHC correspond to something like 10 to the minus 10 seconds back into the beginning of the universe. Now, people, when they hear that, they worry that we're going to create new universes and so on. Don't worry, because the universe is a heck of a lot more massive than the stuff we do in the lab. We're just colliding together very, very tiny particles in the lab. But of course, the universe is, the mass of the universe is the mass of the universe. It's not anything like what we're dealing with. Okay, so how do we do, so that gives you a little bit of the flavour of the science. I can certainly answer more questions, and I'll come back a little bit more later on to a bit more of that. But how do we do it? Well, we do it at Cern, which is now really the world's leading particle physics lab, and at the apparatus called the Large Hadron Collider. And you get I'll show you this picture again a bit later, but you get a glimpse of what the LHC itself looks like on that picture. So Cern itself is an international laboratory. It's covered by a treaty. Somebody was asking me earlier, I think it's 1954 means it's older than the EU. So it was 12 European states when it was formed, and today it has 21 member states. And if you stare at the list of states, you'll realize Israel has joined, for example, which is right on the boundary of Europe, and the candidate states, people trying to join Cern actually now come from well outside Europe. So Cern is becoming very much the world's global particle physics laboratory. The science we do is not cheap. I mean, I'm not going to pretend to you that this is cheap. The budget of Cern is 1 billion Swiss francs per year, and the member states contribute in proportion to their GDP. So for the UK, that's about 14% of the Cern budget comes from the UK. Nonetheless, 1 billion Swiss francs, if you really spread it over a wide enough base of countries involved, of course, this type of science becomes manageable. So the Cern budget pays for the provision and the maintenance of the accelerators and the facilities, and also pays the salaries of about 2,000 Cern employees. And let me stress that before I go on, these guys are nearly all engineers. The 2,000 employees at Cern, they're really very strongly engineers and technical support for the experiments rather than physicists. There's only about 100 physicists employed at Cern. So nearly all of the people who work at Cern on the experiments are funded, come from universities and research labs around the world, and they are funded by those funding agencies. Okay, I won't say anything more about funding, but there's one slide on funding. So this is the Large Hadron Collider. Well, actually it isn't. This is the Swiss-French border, the landscape, and the Large Hadron Collider is drawn on here, but it's actually 100 meters underground, more or less. So you see the size of the ring. If you don't know this area, there's Lake Geneva up in the top right-hand corner, and the runway of Geneva Airport is here on the left-hand side, and the full length of this runway is to about here. So you can see that the LHC ring is larger. I mean, the radius of the ring is about the same as the length of the main runway at Geneva Airport. You can see a little bit on this picture that there's more than one ring here, and I show you that more on this. So Cern, having been there since the 1950s, of course, it has not always been running the LHC. The LHC is the latest accelerator, and there are many other accelerators which have been run from early times. And so one of the first is an accelerator, the PS, the Proton Synchrotron, which started running in 1959. We still use it. And this is one of the reasons why we always do experiments at Cern. It's because we use the previous accelerators, the previous generations, as injectors. They allow us to accelerate particles from a standing start, basically, up to intermediate energies, and that allows us then to put them into the bigger rings. And so this infrastructure that's there at Cern is the reason why, over generations now, we've been talking about the world's biggest particle physics lab being at Cern, or one of the biggest being at Cern. And so really, we build on that. Okay, so let's go down into the tunnel. So this is 100 meters underground, and this is typically what you would see in the LHC tunnel, in a relatively clean part of the LHC tunnel. And What you see here, you see this blue object. Now, around Cern, if you get a chance to visit Cern, you see lots of these blue objects sitting around. These blue objects are 14 meter long, and they're actually the superconducting main dipoles of the LHC. So each of these dipoles, there are 1,232 of these, and they go all the way around the ring. And they provide a vertical magnetic field. It's actually up on one beam and down on the other. And that bends the protons. The protons which are going around the LHC have very high energies, but if you put them in a magnetic field, they bend. And so that allows you to get them to go around in the ring. And so here you can see, if you look up here, you can see that there is a curvature on the ring. Actually, when you're there, it looks fairly straight, but of course there is a curvature. And the radius of curvature is large because it's going to take 27 kilometers to come around in a loop. So each of these superconducting, this one is not superconducting at this point, this is during the installation, but each one of these is a superconducting magnet. Let me show you the more detail of the magnet. So here you see a cutaway, a schematic view of one of the superconducting main dipoles of the LHC. There's really a lot of engineering in these devices. I mean, the radial size of one of these is about this size. So that, and actually this size, the outer container, the blue thing here, this is actually a vacuum vessel. So everything inside there is in a vacuum, and most of the vacuum in there is for insulation in order to insulate the very cold temperatures which are needed for the superconducting dipoles. So the superconducting dipoles are 1.9 Kelvin, 1.9 degrees above absolute zero. The peak field that's produced is about 8 Teslas. And in total, in the whole machine, we need a lot of liquid helium. So liquid helium, you may be used to thinking of something you have in a small experiment in a lab. In the LHC, we have 90 tons of liquid helium at any one time in the machine, distributed around this 27 kilometers. So it's again, there's really a lot of work that goes into the cryogenics and the technology of the cryogenics. In each of the beams, and the two beams are separated in these two beam channels for most of the ring, there are 2,800 bunches, about 3,000 bunches, but each one holds about 100 billion protons. And these guys are what we bring together to collide at the interaction points. So this is actually rather an old picture. This is a picture of one of the pieces of the LHC. This is one of the magnets of the LHC. It's not a dipole, it's a quadrupole. But this is a photo of it being lowered down to the LHC. Every magnet in the LHC, all 27 kilometers, went down the same hole in the ground and then was shipped around this 27 kilometer ring. And this is one of these quadrupoles actually being readied in the early 2000s for installation into the machine. Okay, so you see the people working on it there. You get a feel for the scale. Okay, another thing that people often don't talk about when they talk about the LHC, but in terms of how the experiments operate, this is really a fundamentally important piece, is the beam dump. So we put the beam into the machine, we accelerate the protons up to high energy, and then they contain a lot of energy. They contain about 362 megajoules in each of the two beams. And if you work that out into look at kinetic energy of a moving object, it's about the same as a French TGV train, not moving at full speed, but moving at about half speed, about 150 kilometers an hour. So this is a lot of energy, and when the beam has been used and we want to get rid of it, we have to get rid of it safely. If we just lost it somewhere into the tunnels, it would take many months to recover. So there is a system called the LHC beam dump system, which cannot fail, because if it failed, we would be off for many months, if not for years. And so it's a very complex, multiple redundant system. And so this actually is one of the reasons, when you hear on the BBC or wherever the LHC has started up again, you don't have to wait a long time before people say we have lots of results. One of the reasons is because every time we turn on again, we have to make sure that the beam dump system and every component of the beam dump system is working well. So this is another very important piece of engineering. Okay, there's a huge complex of concrete blocks and all sorts of graphite and so on that absorbs the beam in there. Okay, so this is the view of the LHC, and now I've overlaid the 4 large experiments at the LHC on here. They're all actually down 100 meters underground. I'm only going to talk about one of those, which is my experiment, which is ATLAS. But here in Birmingham, I should mention, we also work on both the ALICE and LHCb experiments, as well as ATLAS. And they do somewhat complementary physics. We look in different ways at the LHC collisions. Okay, so let me come to ATLAS, the detector in collaboration. This is, the ATLAS itself is, the same word is used for two features. It's both, we talk about the experiment being ATLAS, but also the collaboration is ATLAS. So it's the whole thing together. And so ATLAS itself is an experiment I'll show you in more detail, but it sits in a cavern, and this cavern is it's actually about 95 meters below ground at one of the sites. It's actually just across the road from Cern. And if you get a chance to visit there, if you see this huge great building outside, the Globe of Innovation, ATLAS is just behind that. So a brief history of ATLAS. And I show this mainly to make it clear this not only in terms of the large scale of the collaborations in terms of width, number of people, but also we have a very long time scale for this type of physics. It's not something you can do in a year. So ATLAS itself, the collaboration was formed way back in 1992, what's now nearly 25 years ago. Birmingham was already involved in ATLAS at that point. Construction started in 1997 of the components, and the components were built really around the world, including here. And then the cavern underground became available in 2003, and then we've been taking collisions since 2009. And you probably, or some of you with good memories will remember, there was this thing called Big Bang Day that the BBC ran in 2008, which was actually just before we had a problem. So there are problems with this, but nonetheless, a year later we came back in 2009, and everything has worked very, very well since then. And given the 20 years, 25 years to design, construct this type of experiment, of course, we're not going to run it for 2 years and then switch it off. There's lots of physics we can continue to do. In fact, as I'll say later, there's a really nice longer-term program, and we expect ATLAS to continue to about 2035. Okay, so this is the view of the cavern, actually, I think at the end of 2002, when the cavern was still empty. You stare at that and there's almost no sense of scale, but then you realize there are two people down here, this guy and this guy. So they are surveyors measuring the cavern at the time. So the cavern is really quite big. It's bigger than, I think the comparison is it's bigger than the name of Notre Dame Cathedral in Paris. So then, sorry, there was supposed to be an animation here, but it didn't work. So this is actually a picture you may have seen. This often gets shown on the BBC, and they say this is the LHC. It isn't. This is ATLAS. Okay, and it's actually ATLAS during construction. So what you can see here is that there are these things with orange hoops on them. These are a very important part of ATLAS, which is very individual. These are actually superconducting magnet coils again. So they provide very high magnetic fields that circulate around the experiment. And this was taken very early, actually, in the construction. If you go down now, it doesn't look at all like this because there's many, many more components installed. But nonetheless, this somehow has become the very iconic picture for the LHC. So the detector in the cavern, this is a zoom in of the very little picture you saw earlier. And these people here are actually drawn correctly to scale. Okay, so this is about 45 meters long, about 25 meters diameter. It weighs about 7,000 tons, which if you think about it, is actually quite light for something like this. There's actually quite a lot of air in here. It's not all metal. It has about 100 million channels of electronics. Now, that 100 million sounds a lot, but if you think of a digital camera, or even your phone, you've probably got a 10 megapixel camera in there, or you've probably got cameras of around 10 megapixels. That's 10 million channels of electronics. So in terms of number of channels of electronics, today, when we designed it, this was a heck of a lot, but now it's not so much. 100 million is not so large. It's like having 10 phones next to each other. However, the timing, of course, is a bit different. It's a bit more complicated because in your phone, you can maybe take a few pictures per second. In ATLAS, we can register particles from collisions 40 million times a second. So we can take we have a huge capability to separate things in time as well as in space. And of course, the size of the experiment is primarily because we need large distances to see very high energy particles, to absorb their energies, and to see the particles bending in the magnetic fields. Okay, so this is actually, I couldn't resist showing one of these because this is a couple of days ago. This is the Atlas Cavern a couple of days ago. You see these guys with the hoops. So these are the toroids, the barrel toroids. There's actually another piece in here which is a so-called end-cap toroid. And then actually here you see a black cone with a C on it. The C means seaside, which means the right-hand side of Atlas. And this cone is the beam pipe. So that's evacuated, and through there is where the protons go. And then they collide together at the center of the experiment. So here, of course, there's one beam pipe, not two, because the protons have got to collide together in the center of the experiment. The center of the experiment is off in this direction, about 20 meters away. Okay, so this, I show this just because I can't go through the details of course, the technologies used in the experiment. But I wanted to mention this particular piece, which is right in the middle of the detector. So this is what we call the Pixel Detector. It's actually the sensors in here that measure the particles as they go through. It's very, very similar to the technology you have in your cameras or in the cameras on your phones. It's faster and it's a lot more radiation hard, but basically it's not very different. As you can see, it has a lot more cables. Your phone would look a bit silly if it had that many cables, but that's so we can get the signals out so very fast out of the detector. And we took this out actually during the last shutdown of a couple of year-long shutdown, and then did some repairs and changes and then put it back in again. And this is just as it was going back in. But you can see inside the experiment the pieces are not so large. Okay, so then a bit on why we have the multiple layers in ATLAS. So I won't go through this in great detail, but I want to stress that different types of particles that can be produced in the interactions, which happen right here at the center of the detector. This is a sector through the detector. Of course, it goes around. The different types of particles interact in different ways in the detector, and from that we can distinguish between different types of particles. And I just want to emphasize here this guy, the one in orange, which is a muon. Remember, this is one of the fundamental particles in the Standard Model, the heavy partner of the electron. And in fact, in ATLAS, this one's quite different to all the others because it just goes straight through all of the time. It goes right through the detector, which makes it a very characteristic event to look for, very characteristic type of particle to look for. And so I show an event here. This is a real collision event. This is a cutaway view of the ATLAS detector. The collision happened right here at the center of the detector, and then particles were produced and streamed out from the interaction point, or flew out from the interaction point. And two of them, picked out in red here, went right through to the outside of the experiment. So this guy, from the diagram I showed you before, you know these two guys are muons. Okay, so we can measure the properties of these muons. We can see these tracks are very straight in this picture, which actually means they're very high energy particles because they don't bend much in a magnetic field. And so we can actually, from the measured properties of these two muons, we can actually say if there were a single particle that decayed to those two muons, right at the interaction point, when the collision happened, what would the mass of that particle be? And in this case, it's the mass of a Z particle, which was discovered at Cern back in the UA1 experiment, actually back in the early 80s. So in this particular case, this is a very early event. You can see the date is 2010, but nonetheless, this is a beautiful event with two muons. It shows very clearly the type of signature we're looking for, and this type of event is very, very unusual. This happens maybe 1 in a million collisions that you actually get Zs produced decaying like this. So this is the type of signature of nice, high-energy, interesting events that we can look at, we can trigger on, we can take these events. I'll say a bit more about the trigger. This is a similar type of event. In this case, this particle is identified as an electron with the track pointing to it. And in this case, there's actually not an energetic particle going off the other way, so we can reconstruct that actually probably there was a particle that went off there that didn't interact. This is another technique that we use, so we can be sensitive to particles like neutrinos that don't interact. Okay, so how do we do this type of science in terms of the collaborations? Well, ATLAS is a global collaboration, as I've said. It actually has 180 institutions now. We were 178 2 weeks ago, but we had 2 more joining, which were from Austin in Texas and National Tsinghua University in Taiwan, just to show you the global nature. We have about 2,900 to 3,000 scientific authors, including about 1,000 students on the experiment, and this is the list of the institutions. If you look at that for a while, you will see that they really do come from all over the world. I mean, we really do have the people. I mean, the countries, the institutes of the countries are shown, picked out in yellow, I guess it is on there. So just to come back much more locally in terms of the group here in Birmingham. So here in Birmingham, there's 30 of us who work on ATLAS, which if you think about it, there's 3,000 people in ATLAS. So we're 1% of the collaboration, which actually makes us one of the bigger groups on ATLAS. I think we're the largest of the UK groups, at least in terms of one of the metrics. And so here are the happy smiling faces, and some of these people I know are in the audience. I can see one of them over there, but there's plenty of these people in the audience. So this is the team here in Birmingham, and what we have been working on here in Birmingham is actually quite extensive with 30 people over the years. Of course, we can work on lots of things, but as an example, we work on this so-called online event selection, the so-called trigger system, which decides very fast which of 1 in 1,000 collision events we keep. We also work on the particle tracker, where we built 600 hybrids for the hybrid circuits for the readout of this tracker here in Birmingham, down in the basement. You see here some of the wire bonding going on for that tracker. And we also, of course, are very much involved with physics analysis, and particularly some people in the group have been very strongly involved with the analysis leading to the Higgs discovery, and many more things which I don't have time to go into. One of them is the worldwide computing grid. So in Atlas, we rely on having computing all around the world in order to be able to do the science we do. We have about 200 computer centers around the world, and we write petabytes, tens of petabytes of data each year. Now, petabytes probably don't mean much to most of you, but a petabyte is 1,000 terabytes. And if you compare it with the size of the data, this is actually from 2012, so it's a little bit out of date. But if you compare it with the size of data, for example, on Facebook or that's used in Google searches, it's basically a very similar size. The current Atlas data set is a similar size to these very large commercial databases. Okay, so maybe I say a little about how we do the physics at the LHC. Okay, so when we collide the protons together, the protons collide all the time. We get 1 billion interactions per second. So the rate of events per second is shown on this axis. And on this axis is the energy of the collision. So you only have to focus on a couple of lines, which are these two, which is what's happening at the LHC. And what you see is the total cross-section. So how many interactions we get per second is shown by this 10 to the 9 number over here. That's the 1 billion interactions per second. If we're looking for something, this was drawn before we knew what the mass of the Higgs was, but if we knew what the Higgs is about 120 GeV, there's about 1 Higgs particle produced per second. Okay, so our computing systems allow us to write about 1,000 interesting events per second. I showed you W's and Z's, which are about 1,000 per second. So we sort of saturate the data we can write with the W's and Z's. But we can take the Higgses. This, of course, is what we need to do. Okay, let me go very fast through this one. So the crucial thing in the data that we get is we need to see events. We need to see new types of events, and we need to see a lot of them. This is really what we're trying to do, because then we can, first of all, we can discover new things, perhaps, and we can study the events we produce. And that's controlled by this equation. I only have one equation in this talk, and it's not E equals mc squared. It's this one. And that tells us how many events we observe, and it's a product of 3 factors. And the 3 factors are a thing called the cross-section, which is given by nature, a thing that's an experimental efficiency, which tells you how well we've built our experiment, and then a thing called the integrated luminosity, which comes from the LHC performance. Now, as experimentalists, we spend a lot of time optimizing this, trying to make this as high as possible to get as many events as possible. But of course, ultimately, what really matters is the integrated luminosity, how the machine is able, the accelerator, the LHC, is able to deliver collisions to us. And so the amount of data we've collected as a function of time is shown in this plot for different years. And you see in 2010, it was almost invisible. Nonetheless, we could do lots of interesting studies. But of course, 2011, 2012 were really the big data-taking years from the so-called Run 1 period when we had this lower center of mass energy. Okay, that I can skip. So with the Run 1 data, we've measured lots and lots of processes. So I talked about W's and Z's. I talked about inclusive proton collisions. I also will come to talk about the Higgs. But basically, we were able to measure many, many processes over many, many orders of magnitude of rate. Really huge number of orders of magnitude. So from 10 to the 14, from the highest to the lowest. We were able to measure all of these processes. We do it, and we see lots of things which look very largely as we expect, in fact, in most of these cases. But of course, we're looking for deviations. So let me skip that guy. So let me come to one example which you've all heard about, or I'm sure by the fact you're here, you've heard about this one, which is the Higgs boson. So of course, in Run 1, in this first data-taking period from 2010 to 2012, the main new thing that came up was the Higgs. So to introduce the Higgs to you, we know the standard model itself predicts if we have a Higgs with a mass of 125 GeV, which we now know, we know how often, when we've produced these particles, they decay in different ways. So they will, very fast in the detector, they will fall apart, they will decay into different particles. And the most common one by far, more than half of the time, is decays into B quarks. So these are fundamental heavy partners of the up quark. However, this guy, we haven't seen. Okay, we have some attempt to see those, but we haven't seen those in the experiment. We haven't seen Higgs to BB decays. And that's because it's actually, there's these billion events per second going on, and picking out these events is very, very difficult. These guys look just like many of the so-called the backgrounds. But if we look over here at the relatively small numbers, there's a case 3% of the time that Higgs decays into 2 Z particles. Now, I showed you the Z particles. They're beautifully clear. And so finding the Higgs decaying into Z particles, the rate is very low, but it's really easy in comparison to finding it decaying into these guys. And then there's another guy, which is actually even only 0.2% of the time when the Higgs decays into 2 photons. The gamma here is a photon, the carrier of the electron. electromagnetic force. So these two guys, it turns out, are the so-called golden channels. These are the ones we looked for to try and see the Higgs. And so here you see a Higgs to gamma-gamma event. And so what we did in this particular case, and it's worth paying attention here because I'll come back to gamma-gamma mass spectra later in the talk, but what we did was we looked at many events, and we looked to see events where we saw two things that look like photons, which are these deposits of energy with no track pointing to them. And we said, okay, how often do we see those events with certain characteristics that look as though they came from a certain type of particle with a specific mass? And then we plotted that all the way across as a function of the mass of this particle. And we saw that first of all, there's a big background, so you see there's many sources of such particles, but there is, in a certain place, there's an excess over with a smooth background. And so if you fit that with a smooth curve and allow a bump to be there, you see that there is a bump, and that bump is actually quite significant by now. And that bump in this smooth mass distribution is the signature that something else is going on. It tells you, now it tells us that this is due to a new particle being produced and decaying. But you can see it's very far from the only source of events like this. In fact, it doesn't happen. Most of the events in this distribution, something like 999 out of 1,000 of the diphoton events are actually not in here. They're in the rest of the distribution. But nonetheless, because there's this localized cluster of events, more than you expect in a certain mass region, this allows us to get a handle on it. And then in the 4-lepton case, which is the case of the 2Z decays, we can do a similar thing. And here, the background is much, much lower because of these beautiful clean signatures of Z events. But again, we look as a function of the mass of an object that decays and say, if there was a single object that decayed to 4 leptons that we see, 4 electrons, 4 muons, 2 electrons, 2 muons, what was the mass of that object? And our expectation is shown by the red curve here, without a Higgs. And what we saw was that there is this clustering of events at a particular mass, at 125 GeV. So in this case, this is another smoking gun to say that there is something going on here. And the fact that this mass, 125 GeV, in this process is the same mass as in this process really tells us that there's a new particle here. So it's a particle which in the two different decay modes has the same mass because it's the same initial particle that decays in two different ways. Okay, so that's a 4-lepton decay. Now, I have a problem on this slide because I can't show it to you because it was supposed to cover up. So I won't tell you what's on the slide behind, but let me summarize what this slide says, which is that by the time we got to July 2012, looking at all of the different possible masses for a Higgs, we looked to say, do we see anything there that doesn't look just like background? And of course, when you see a bump like that, it doesn't look just like background. And we then make a statistical test which says, how unlikely is it that the background could have given us that bump, or those two bumps in this case? And the answer that we got in July 2012 was about 1 in 500 million. So if we did 500 million experiments, only once would we see something of significance, if it was just due to background. So this is extremely unlikely, and this is what we call a 5 sigma effect. And so this is when we talked about the 5 sigma discovery of the Higgs. This is because the probability of a background fluctuating to give us something that looks like what we saw in the data is so unlikely. So this was the situation in July 2012, and not only did we see 5 sigma in ATLAS, but CMS on the other side of the LHC ring also saw 5 sigma, and then, miracle of miracles, the masses were the same, and we did these analyses independently. So this really tells us we had 2 channels with significant observations, and then we had 2 different experiments, and in all 4 channels, all 4 cases of 2 channels, 2 experiments, it all looked like the same mass. So this was partly, although we had 5 sigmas, we also had this coincidence of masses, which made it very clear that we had discovered a new particle. And so this is a picture from July the 4th. This is the main auditorium at Cern. Some of you may have seen the pictures from this. It was a really fantastic event because Peter Higgs and Francois Engler is here actually, were both at this seminar. And it was a very emotional occasion. I have to say, this is one of my eternal regrets. I drew the short straw because this seminar was the first day of the biggest international conference of the year, which happened to be in Melbourne that year. And I got the short straw, and I was in Melbourne. So we had a live webcast, and so it was 9 o'clock in the morning at Cern so that we could join it at 5 o'clock in the evening from Melbourne. But nonetheless, it was really, in both places, it was really a fantastic celebration. And let me mention that My predecessor as spokesperson at Atlas is Fabiola Gianotti, who's here presenting it, but her predecessor as spokesperson is actually this chap who was sitting next to me in Melbourne, P.T. Yenny. So I wasn't the only one out there in Melbourne. Okay, this clearly, I mean, as you're aware, this really caught the imagination of people around the world, and this was particularly striking when we traveled halfway around the world in order to see this conference, because we saw, as you went through newsstands in airports around the world, that we were on the front page of newspapers all around the world. It was really caught the imagination of people, of the general public, and I think this was really a fantastic thing for science in general, that people appreciated that there are these big advances that are made. And of course, then this was rewarded by the 2013 Nobel Prize in Physics to Englert and Higgs. Unfortunately, Brout has passed away, so he couldn't share it. Okay, now since the discovery of the Higgs, we've been continuing to look at it. We've been collecting more data. And so now one of the things, what's shown on this is just, we look at how often the Higgs is decaying in the different decay modes, and we try to see if it's consistent with our expectation, because this is one of the predictions of the Standard Model Higgs. And basically what you see on this straight line is it does agree pretty well. But there's a whopping great error bar on this one here for the B, and that's because we haven't actually seen that very convincingly yet. Okay, so I've mentioned the Higgs as part of the scientific haul of the first 3 or 4 years of operation of the LHC. We have a huge amount more. So from Atlas, we now have 505 publications based on Run 1 data. There's more than 1,000 in total from all of the LHC experiments put together. And I can't talk about all of those results, but there's a huge number of very interesting measurements, a lot of searches for other new physics beyond the Standard Model, but as you will realize, those have all turned up a blank so far with the Run 1 data. Okay, so what's next? What's next? Okay, well, sometimes you hear people say, particularly perhaps people who are not favorable to particle physics, it's the end of physics, it's all solved. The Standard Model predicted the Higgs and we found it. Well, perhaps. But there's really so many questions left in the Standard Model. And indeed in the universe in general, there are many questions left. So why are there these 3 families of leptons and quarks? No idea. We have no idea. Why do they have such different masses? So the mass of an electron is, if I get this number right, it's always hard off the top of my head, but it's something like a 1/200,000th of the mass of a top quark. There's a huge hierarchy in masses, very, very different masses of these particles. So we know how to make the masses using the Higgs, but we don't know why the values are so different. Is there more unification of forces? We don't know. What is the dark matter in the universe? I'll say more about that in a moment. There's also a big matter-antimatter asymmetry in the universe. The laws of physics are almost symmetric between matter and antimatter. We think the initial conditions in the Big Bang would have been symmetric between matter and antimatter, but if you look around you, where's the antimatter? The antimatter's all gone, so again, a big question. And then there are also ideas, which is probably we should save for the drinks, but there's also ideas that maybe there are extra dimensions of space and time about to show up. So there's many questions. Where and what comes next? And in fact, the observation of the Higgs has just really crystallized these questions. They really are a bit more clear, or at least clear that there is really a big problem here. So dark matter in the universe, I'm not an astronomer, I should say, but nonetheless, the dark matter, there is a lot of evidence for dark matter in the universe. And if one looks, for example, and this was done a long time ago, one can look at galactic rotation curves. I think this was first Zwicky back in maybe the 50s or something like this. They looked at galactic rotation curves. They looked at how fast stars were rotating around galaxies. And they see that the distribution of matter in the galaxy doesn't follow the distribution of the visible matter in the galaxy. So it looks as though there's some extra matter there, which is dark, which is where dark matter came from originally. If we look at clusters of galaxies, this is a Hubble Space Telescope picture, I think. There's an effect gravitational lensing, which means that this huge great galaxy in the middle, there's actually other galaxies behind it which are emitting light, and you can see it actually from these, this lensed effect. You can see the light from these much further galaxies, and we can check that it really is from the further galaxies. And again, if you do that, there's much more matter there than there seems to be in those galaxies. And so from this and a range of other measurements, which would be a seminar in themselves, we now believe that the universe is made up only of about 5%, the normal everyday baryonic matter. That means normal everyday matter. But then there's about 25%, which is stuff that we don't know what it is. I mean, we know it's matter of some sort, but it doesn't seem to be any of the particles we know about. And then there's another 70%, which we really don't have much clue about at all, which is the so-called dark energy. So most of our universe is missing. I mean, we really do only understand about 5% of the universe very well, and this is a big problem. And the issue of non-baryonic dark matter is one which probably, or we're trying to access in the LHC. And there is this theory, which I will be very fast on, but there's a theory called supersymmetry, SUSY. You often hear people talk about this. There are some real devotees of this theory. But this says for all of the particles we've got, there's actually another particle behind it, a so-called supersymmetric shadow particle. Now, the catch with supersymmetry is, okay, if there's all these other particles, where are they? We've not seen them yet. But maybe they're much more massive and we haven't discovered them yet. Who knows, maybe. But supersymmetry has one really great feature in this type of analysis, that it gives a very natural explanation of what the dark matter particle could be. It would be the lightest supersymmetric particle, the so-called LSP. And it should have, based on the models of the early universe and evolution, it should have a mass which is accessible at the LHC. So this is something that we are looking for, certainly very hard all of the time. But this is actually just one type of a new beyond the standard model hypothesis, so-called, to try and explain some of these remaining questions. But really, we don't know which of those is going to show up first, and so really we are searching everywhere we can, and the standard expression we always have these days in Atlas is we're really searching eyes wide open. We're looking everywhere we possibly can, in many tens, if not hundreds, of different event types to see if we can see things which don't look like the standard model. Okay, so we've also shifted the energy of the accelerator up from run 1 to the latest data taking, run 2, from 8 to 13 TeV. And when we do that, these processes, these are all hypothetical processes that I've put inside the ring, and you get a boost in rate of these processes, which is somewhere between a factor 4 and a factor of 50. And so if any of these guys are there, it's so much easier to see them. We'll make so many more of them, 50 times more, 20 times more, 10 times more, depending on the process, than we did in run 1. So we have a huge additional possibility to see these new processes. Okay, unfortunately I can't explain in detail what all of those are, but these are all of these new possible models of new physics. So we started at 13 TeV. This is now back in June last year. This is the first day of physics collisions at 13 TeV. This was back in June last year. To get there at 13 TeV, this required a 2-year shutdown of the LHC in order to repair the magnets, basically, to make sure that this problem that we had in 2008 couldn't recur. But that's now all fixed, and the machine is running very well up to 13 TeV. I can't resist showing this one, because this is the Atlas control room, so these are all my friends. So this guy here is worth pointing out particularly. If he looks sort of very... It's because this guy is one of our 2 run coordinators in Atlas, so he's the guy who's responsible for making sure we take data. So the fact that he's looking as though things are going well is a very good sign. Okay, these people in the front actually are also a good sign, because these are trigger experts. Okay, and so run 2, the data taking with this higher energy, what we call run 2, this has just started. So although we've run in 2015, remember, every time we start the accelerator again, we have to make sure the beam dump system, et cetera, is working well. And so it was a very slow start, but then later in the year, we started to ramp up more collisions, many more collisions. But so far, with the amount of collisions we've got there, in terms of total number of proton-proton collisions, we only have about 1/6 of the collisions in run 1. And so there's really still a long way to go in run 1. We've just started to scratch the surface of what may be there. And in 2016, we expect to basically to have the same as the whole of run 1 again. But then in addition, if a process has 10 times as high a cross-section, we'll have 10 times more events than we did in run 1. Of course, if the cross-section is 10 times higher and you only have 1/6 of the data, you don't have such a good chance of seeing something new. So again, it's really, although you hear about the LHC operation and the fact that we've started to take data, we've only just started. Again, it's a multi-year program. Okay, so we've made measurements of various different particle productions at this new center of mass energy, and what you see immediately is these look as though they're reasonably well described, which is good. That establishes that things basically are working at the new center of mass energy. And then we start looking beyond. Now, with the data sample we've got, we don't have a lot of sensitivity yet with the 2015 data beyond the standard model, but nonetheless, you may have seen in the press, and this is from the BBC website, sometimes the way these things are explained in the press is intriguing to scientists, but the world of particle physics is currently buzzing with excitement. In December, physicists at Cern announced the first significant results since the LHC was restarted, which is true. We had a seminar on the 14th of December. And then in the eagerly awaited talks, which is certainly also true, the 2 experiments that discovered the Higgs boson reported hints of a new elementary particle. Well, is that true? We don't know yet, to be honest, but maybe. So I show you just this one distribution, since this has caught the press's imagination. I show you this one distribution. So if you remember the gamma-gamma mass distribution where we saw the Higgs, that was between 100 and 150 GeV, so relatively low mass particle. 125 GeV Higgs was what we found. Here we're looking at much higher masses. Okay, so this is this is 10 times the mass of the Higgs. It's about here. And then this peculiar feature has showed up in the distribution, which we don't at this point really know how to interpret. But since this is the data, these are the data we want to show it, you see that there's something here that starts to look a bit like the Higgs did in the early days. However, the significance of this is way off the 5 sigma benchmark that we talk about. The significance of this is between 2 and 3 sigma at the moment. We need a lot more data to figure out if this is really going to be there still with 5 sigma. But it's got people excited, particularly, I'm an experimentalist, of course, working on the experiments, but we have our theoretical colleagues where there's a community, and there are 175 papers that they've written on this one particular 2 sigma bump. So you can see why it's causing a lot of excitement, but it's far too early, I think, to say that this is definitely something new. Quite likely when we turn on the LHC again and we take a lot more data, this thing will go away. History tells us, this is why we always look for 5 sigma, history tells us that humps and bumps often occur, but then go away with more data, just because of statistics, just because you don't have enough data to understand it. So will this go away? We don't know, but it's interesting to watch the space for another 6 months to a year. Okay, so further into the future, I think I'm more or less running out of time, so let me not spend much on this. But I did say at the start, the LHC has a long program ahead of it. And so the first part is this so-called run 2, which is happening now. This is a very complicated diagram, but the green parts are good. That's when we're running and taking data. The blue parts are not so good. This is when the accelerator is stopped because we're working on the accelerator or the experiments. And so run 2 will run through until the end of 2018. We should get about 4 times the amount of data we had in run 1 in total. Then we will up the energy a little bit more, up to 14 TeV, we expect to, and then we'll run for run 3 for a few years. And then we'll have a long shutdown. We'll upgrade the experiments, and then we'll run again for a much longer period with much higher intensities in that period. So we won't increase the energy further, but we increase the intensity much more, which gives us many more events and allows us to look with much higher precision at things. So there's a whole program that's started now. We're very much involved here in Birmingham to upgrade the detectors, basically mainly for this period in about 2025. So on our timescales, we know from the original detector construction, we need to start building detectors about 7 or 8 years before we actually need them. And so we're starting this work now. Okay, I think I skipped that one. This just shows you a beautiful simulated picture of an event at 200, well, at the HLLHC luminosities. So in this case, there's actually 200 collisions have happened at the interaction point all at the same time, 200 proton-proton collisions. But although this looks like a complete mess when you just look at it, the precision of our detectors and the granularity of our detectors mean we can disentangle what's gone on here. We can separate out the products from the 200 different collisions, or at least most of them. And so we will be able to do physics with this type of collision, but it does require upgrades to the detectors. It also requires upgrades to the machine, and here I just flash one picture, which this is actually a zoom in around the Atlas Cavern. You see the accelerator tunnel, the LHC tunnel, which goes right through the middle, and actually a lot of civil engineering and then installation of different components to make sure the beams are much more tightly squeezed when they collide to get these very high intensities. This also has to take place, and this will be actually largely happening already in the next 5 years. So there's really big programs of work for the LHC upgrades. This is all now basically approved by the member states of Cern that this will happen. Okay, so let me just then come to some closing words. I hope I've shown you that the LHC, the Cern LHC and the experiments are really global endeavors, and they were 20 years in the making, and they'll be 20 years in the data taking. From this first run, this first low energy run of the LHC, we made many measurements establishing that the standard model is still going strong, and what's more, discovering this new final missing link in the standard model. But that really opens up a lot of new questions about what's going to come next and what we're going to see when we up the energy further. And so we started with this step up in energy to 13 TeV. But really, there's much more to come in the next months and years, and really we're headed once more into the unknown in fundamental physics. Thank you. Yes, so I mentioned there are about 100 physicists. So there are teams of physicists, small teams of physicists at CERN involved in the experiments, but you can imagine the team of physicists involved in ATLAS is actually not much bigger than the team from Birmingham involved in ATLAS. It's a bit bigger. But then there's a lot of engineers, and the engineers work on the experiments, but they largely work on the accelerator. So CERN's main function at some level is to make sure that the accelerator is there, working, and that the infrastructure is there that allows us to build and operate the experiments. And so that's really the work of that's the primary work of most of the CERN people. Of course, there's also then a lot of administrators, people who provide coffee and so. I mean, really, it's a laboratory, and so of course there has to be just more general infrastructure as well. But the key things that CERN do is really provide the accelerator infrastructure. Now, when I showed the picture of the accelerators, I sort of simplified because I said these old ones are just injectors for the LHC. There are a lot more than that, actually, because there are still a lot of experiments running at those older accelerators. There's still interesting physics to be done at those. So there's actually a very wide spread of physics that goes on at CERN beyond the LHC. Yes. Yes, so in terms of particle physics, as with every specialized field, there tends to be quite a specialized jargon. Now, I hope I tried to remove most of it, but I probably didn't succeed. I'm sorry for that. But there's also language gap in another sense. There's the language gap of, because we have people from all around the world, our language, working language is always English. At least for all of the scientific part, it's always English. But of course, there is an issue with people from other parts of the world. They're quite disadvantaged in terms of being able to communicate freely in English in many cases, often not in many cases. And so it is, we do try to work hard to make sure that things are accessible for everybody. I mean, it's clear that we need to get the most out of everybody in ATLAS. I mean, we really have to provide an environment where people can really do the science they want to do, even if they're struggling to communicate in English, for example. Another thing we always do, which you saw the map of the globe, I mean, you may get the impression that everybody sits at CERN to do these experiments. We don't. We have, of the 3,000 people, we have about 300 or 400 people who are based at CERN on the experiment, who are not, most of them are not CERN staff. And the other 2,600 are in their institutes all around the world. And people can work there. The data is actually distributed around the world on the grid at these sites. And so people can work from there. Every meeting we ever have in ATLAS, there's always a video conference. This is one of our #1 rules. Every meeting has a video conference. So wherever you are in the world, you can always join a meeting. Except it might be in the middle of the night, of course, but you can join it. If you're awake, you can join it. Yeah, it's the energy. Yeah. So we tend to talk about energy rather than speed, just because the particles are all going very close to the speed of light, and so the speed is it gets to be very close. But the energy of the particles, that's exactly right, because with the field, the magnetic field we can provide in those magnets is limited by the technology, and so at the moment it's 8 Tesla for the LHC. There's work going on to see for future generations if we can do this with 15 Tesla field or something like this. But 8 Tesla field means the bending of a particle as it travels through the magnetic field is dictated by the energy of the particle or the momentum of the particle, the strength of the field, and then the radius. I mean, there's a simple relation between them. And so as you push, if you push the energy up very further, you need a stronger field than 8 Tesla to bend it around a 27-kilometer ring. So yes, it's completely limited by the magnetic field we can have in this size ring, and that limits us to about 14 TeV. Exactly, yes. So it does, by having higher intensity collisions, which is really the long-term program, the very high mass particles, you can still produce them, but much more rarely. If they're still less than 14 TeV in mass, you can still produce them, but much more rarely. And so if you increase the intensities, you can produce more of them. So by increasing the intensity, you do push up a little bit your sensitivity in mass, but not very much. So yeah, if you want to go, the obvious question is if you want to go and build something that's much more energetic, what do you do? Well, first of all, you build much stronger magnetic field, which is really pushing technology, but particularly if you want them over a very long distance. And secondly, you build a bigger tunnel. So there's ideas at CERN to build a 100-kilometer tunnel after the LHC. So this, if we were to do, I mean, it's interesting, tunneling technology, particularly because of the way China has been building so many tunnels, it's much cheaper these days than it used to be. So it cost something like a couple of 3 billion to build a tunnel for LEP, which is now the LHC tunnel. Whereas they think that for more or less the same price, maybe 50% more, they can build a 100-kilometer tunnel because of cheaper tunneling technologies. Yes, this is a long one, which maybe we can continue over drinks, but every paper that Atlas has written on physics has the whole collaboration as authors. Now, that sounds a bit weird. Why don't you just have the people who did the final stages of the analysis? But the answer is, in order to build this scale of experiment and to operate it and to make sure the computing system works and operates it and so on, which you need for every analysis, that needs a large fraction of the collaboration. And so you can't say just the few people who made the final plots that are in the paper should be the ones who sign the paper, because it's not fair to the vast quantity of work which has gone in for the underlying infrastructure. And so partly for that reason, and also partly it's a little bit historical, we have the principle in the large collaborations that people do a certain amount of contributory work to the experiment. We call it typically technical work or something like this, but work really to make sure the experiment is well operating and so on, which is not the final analysis stages. And everybody has to do that, and they have to do a year's work like that, and then once they've done that and they continue to work on the experiment, basically they're qualified as authors for the experiment. And this means that all of our papers have the order of 2,950 authors. This clearly, in terms of metrics and ranking agencies and so on, this causes difficulties. I mean, it's clear that it's a different way of working to some other areas of science. On the other hand, the work which is needed to do these mega science projects, it's different to the thing you do in other areas of science. It's not that a few people come along, build an experiment, and then everybody uses it. I mean, everybody has to work together to get the science out of the experiment. And so it's a difficult thing, and I see that with the LIGO results, it's a very similar thing, that they have a paper with 1,011 authors, I think, on the LIGO, the gravitational waves paper. And it really does reflect the nature of the field. Now then, the question is, how do people get recognition? And so internally, inside the collaboration, we do track the contributions of individuals, both to the operations work, both to the detector work, to analysis, and to other things related to computing, etc. So we have a database, which means we know roughly what people have contributed in which areas and so on. And so some of that information is available, and so it's a constant discussion. We're discussing at the moment how public we want to make that information. It's freely available inside the collaboration, but at the moment we don't make it public externally. But it's a very tricky discussion as to how much we should make that public, because we don't want. The problem is that sometimes the most glamorous work is seen to be making the final plot that shows you've got a bump in the Higgs mass spectrum. But that's actually one of the easiest things to do, of course. The really hard stuff is to make sure that the detector is working correctly, day and night, 24/7, 250, 300 days a year. And so we have to make sure, if we do make the information public, that we make the full info, or that we make really sufficiently detailed information public, that people can understand the contributions of individuals. Now, of course, because the community is, a large fraction of the community is on one of the LHC experiments, of course, there is often the internal information has some accessibility if people are applying for positions or something like this. I mean, there is some, it is possible that there is some access to this type of information, but we don't make it generally completely public.
And the final part was how you referee. I mean,
how we referee.
Can
so
you really
internally,
independently check
because
whether this is
everybody
right?
in the collaboration signs every paper, everybody has chance to comment on every paper. So every paper, the analysis is typically put together, that we have physics groups, which are typically anywhere between about 50 and 500 people. And an analysis is reviewed by the physics group, which typically means there's a big plenary meeting, which maybe has 100 people in it, where you look and talk through the analysis for many hours, often repeated to cycle. Then the draft is circulated to the full collaboration. So we circulate every Atlas paper to the full collaboration, and everybody has a chance to comment. Now, not everybody does comment, unfortunately, but we do get a lot. I mean, it's very variable depending on the interest and how focused the paper is. But we do get feedback from people who you didn't know would be interested in this subject.
I think since I promised people refreshment and also the opportunity to ask questions informally, we should bring the questioning, formal part of the questions to a halt, and it just remains for me to thank Dave very much indeed for giving up your time and giving such an inspiring and interesting talk. Thank you very much.
you.